All right. Good morning. Welcome to my stream. What we did yesterday was we worked on, let's switch over. There we go. We worked on the editor and we got part of the way through section 4. It looks like about maybe not quite halfway, 2/5 maybe. We're able to move the cursor and stuff like that. But today, moving left at the start of the line. Today we're going to switch back to this, crafting interpreters, because we're really close to the end of this book. Unfortunately, the screen is not wide enough. Let me move it over, or look at it over here, crafting interpreters. If I look at it here, we can see approximately where we are. We're in methods and initializers. So we have 3 chapters left to do. And this chapter has declarations, references, this instance initializers, and optimized invocations. Whatever optimized invocations are. Sounds exciting. But we're going to start right off the top with method declarations. So let's make sure we're all clean. Status. We are up to date. There's nothing here. So we're good to go. All right. It's time for our virtual machine. Oh, I got the wrong screen up here. Here we go. To bring its nascent objects to life with behavior. So right now, all we can do with the objects is we have this pair, right, where we can set fields and we can get fields, and that's all we can do. I think we probably can do links, or we can go through it. Let's see. I'll call it nest.locks, because I think we can do this. Class foo, class bar. Right? We can create 2 different classes, and we can say var f equals foo, like that. We can say var b equals bar, like that. And then we can say b dot field equals 12, for example, and we can then say f dot bar equals b. And we can say print f.bar.field. We should be able to do that. So this should output 12. Oh, I forgot to give it the file name. Yeah, so this outputs 12. Now the question I have, if I change field, b.field equals b.field plus 27, will f.bar.field change? And it should, right? Because bar is a reference to b. So it should print out 27 plus 12. And it does. Okay. So that's kind of neat. Where's the add opcode? Here it is. So you can see we're adding 27 to 12. We get 39 on the bar instance. And then we say f dot bar, which gets the bar instances, dot field, which gets the field from bar. So that's all working great. But now we're going to do methods. So that's going to involve parsing code again and creating chunks again, I assume. Methods and methods calls, since they are a special kind of method initializers too. Initializer meaning what? Don't we already have initializers in the sense we can say var x equals 12, right? Doesn't that initialize x? Maybe they mean like constructor initializers. It's like when you oh, that's right, we did that in the locks version where you have an init method. It's automatically called when you initialize the. Yeah. All of this is familiar territory from our previous JLox interpreter. What's new in the second trip is an important optimization we'll implement to make method calls over 7 times faster than our baseline performance. But before we get to that fun, we got to get the basic stuff working. We can't optimize method calls before we have method calls, and we can't call methods without having methods to call, so we'll start with declarations. We usually start in the compiler, but let's knock the object model out first this time. Runtime representation for methods in clocks is similar to that of jlocks. Each class stores a hash table of methods. Keys are method names, and each value is an object closure for the body of the method. So, right, yeah, that's right. Our class is pretty empty right now. It just has a name as a string. But now it looks like we're going to add a hash map of methods. Now the question I have right off the bat is, remember the issue we had with instances, is that I had to make this a ref cell, and then I had to think about, should this be a clone of the value or an RC to the value? And we ended up having to do cloning in order to get stuff, which is unfortunate. But all right, let's just take the naive approach, methods, and just have it a hash table, a hash map of string to value. We could put closure in here directly and just say it's only takes closures. That might be a better way to go. Let's just try. First, we have to include standard collections hash map. We do need to, if we put closure in here, let's see, what does closure look like? I've forgotten already. It's an RC to a function and then a ref cell for the up values. So it doesn't need to be mutable. So we can try sticking the closure in here and see what happens. Only one column, hash map. Yeah. So, oh right, we need to import it. Use create closure. Okay. So that I think is going to be all of that. Keys are method names, right? So it's just going to be strings, and each value is an object closure for the body of the method. We might need to make this a value in order to interact with the VM better, but let's find out. Right, then we have the garbage collector. We don't have to worry about that. Storing classes methods is pretty familiar coming from jlocks. The different part is how that table gets populated. Our previous interpreter had access to the entire ST node for the class declaration and all of the methods it contained. At runtime, the interpreter simply walked that list of declarations. Now every piece of information the compiler wants to shunt over to the runtime has to squeeze through the interface of a flat series of bytecode instructions. How do we take a class declaration which can contain an arbitrarily large set of methods and represent it as bytecode? Let's hop over to the compiler and find out. The last chapter left us with a compiler that parses classes but allows only an empty body. Now we insert a little code to compile a series of method declarations between the braces. So let's go to the compiler. Class declaration. All right, this is pretty basic. So we have consume, expect, oh, right in here. Okay. So this is where the body is. So we do the class name, we identify it, we declare the variable, we emit the bytes for the class name, for the constant, and then we define the variable for the constant, and then we open brace, and now we're going to do the body of the class. This says while check token write brace and not check token EOF method. So we're going to say while we don't see a write brace and not the end of the file, then try to parse a method. Okay. Okay, and I guess we don't have to worry about fields that get set in there because that's not part of the locks. Yeah, here it is. Locks doesn't have field declarations, so anything before the closing brace at the end of the class body must be a method. We stop compiling methods when we hit that final curly, or if we reach the end of the file. The latter check ensures our compiler doesn't get stuck in an infinite loop if the user accidentally forgets the closing brace. The tricky part with compiling a class declaration is that a class may declare any number of methods. Somehow the runtime needs to look up and bind all of them. That would be a lot to pack into a single op class instruction. Instead, so this is interesting. I'm trying to think of what's... Okay. Instead, the bytecode we generate for a class declaration will split the process into a series of instructions. The compiler already emits an op class instruction that creates a new empty class object. Then it emits instructions to store the class in a variable with its name. That's this thing here. Now for each method declaration, we emit a new op method instruction that adds a single method to that class. Interesting. I was kind of assuming that there would be chunks stored in the class itself. Somehow. When all the op method instructions have executed, we're left with a fully formed class. While the user sees a class declaration as a single atomic operation, the VM implements it as a series of mutations. But I think the optimization they're talking about is we should only have to do this once. Once we do it the first time, we should be able to skip over it. We did something similar for closures. The op closure instruction needs to know the type and index for each captured op value. We encoded that using a series of pseudo instructions following the main op closure instruction. Basically a variable number of operands. The VM processes all of those extra bytes immediately when interpreting op closure instruction. Here our approach is a little different because from the VM's perspective, each instruction to define a method is separate standalone operation. Either approach would work. A variable-sized pseudo instruction is possibly marginally faster, but class declarations are rarely in hot loops, so it doesn't matter much. Oh, that's a good point. Yeah, so we're only defining a class once. And once we've done it once, we never have to declare the class again. So it's okay if it's a little bit slow. To define a new method, the VM needs three things: the name of the method, the closure for the method body, and the class to bind the method to. We'll incrementally write compiler code to see how all those get through to the runtime, starting here. All right, so we're going to add this after function. Function's a very long function. Okay, fn method self, and that looks like self consume expect method name, and then let constant is equal self identifier constant. Except I have to do this business here. And I guess it should be parse token constant. And then we just pass in parse token like that, and then we just emit bytes for the method. Self emit bytes. Oh, we need a new opcode. Opcode method, and it takes the constant. So that's easy. Like opget property and other instructions that need names at runtime, the compiler adds the method name tokens lexeme to the constant table, getting back a table index. Then we made an op method instruction with that index as the operand. That's the name. Next is the body. So I won't be able to compile this until we add the method opcode. Function type equals type function type. Did we ever do the function type business? We did chunk type. That's what I called it instead of a function type. I called it chunk type. And where do we use that? Oh, when we initially create a function. Oh, okay. So we're actually... Right, so when we call function, it's function here. All right, this may break at some future point. We might have to actually add a parameter, add a chunk type parameter. Because right now we don't. Right? We just assume every function that we ever call is going to be a function of type function. We do have the script, which is right off the top. Let me see if I can find that. Right. And that's only used for return statement check and can't return from top level code. That's the only reason it's used. And that's default. So when we create a chunk, we automatically get a script unless we specify otherwise. And when we do this new, we get this here. So I think we're good. Where were we? Down here. So we don't have to worry about that. We just call function. Boom, done. We use the same function helper that we wrote for compiling function declarations. That utility function compiles the subsequent parameter list and function body. Then it emits code to create an object closure and leave it on the top of the stack. At runtime, the VM will find the closure there. Last is the class to bind the method to. Where can the VM find that? Unfortunately, by the time we reach the method instruction, we don't know where it is. It could be on the stack if the user declared the stack in a local scope, but a top-level class declaration ends up with an object class in the global variable table. If Lock supported declaring classes only at the top level, the VM could assume that any class could be found by looking it up directly in the global variable table. Alas, because we support local classes, we need to handle that case too. Fear not. The compiler does know the name of the class. We can capture it right after we consume its token. That's up in class declaration. So let's split this. Oops. Class declaration. Oh, it's right here. What am I doing? Okay, so here we're going to save the name. We're saving it here. Class name. That's all we have to do. Wait. We got both of these here. Okay, they're both on screen now. And we know that no other declaration with that name could possibly shadow the class, so we do the easy fix. Before we start binding methods, we emit whatever code is necessary to load the class back onto the top of the stack. So I guess we're calling named variable. Right here. Class name and false. I don't know what the false means. Basher Zombie says, hey, I started reading crafting interpreters recently and wanted to learn Rust. Now I'm following your series on YouTube. Happy to catch you live today. Oh, good. I'm glad you were able to catch me. I hope I live up to your expectations. How far along are you in the crafting interpreters? It's probably not the best way to start learning Rust, but it's certainly a good way to improve beginner Rust skills, to try to port something from C or Java to Rust. Right, so we already have a function called named variable. I remember that. And it takes a token and whether or not we can assign to it. Oh, right, and we can't. So do we have to do that? I can't compile yet because we don't have method. I'll try. Let's see what happens. Oh, right, I changed this to class name. Yeah, we don't have method. Oh, that's the only error. Okay, so so far so good. So far so good. Right before compiling the class body, we call named variable. That helper function generates code to load a variable with the given name onto the stack, and then we compile the methods. Basher says, I wrote a chip 8 emulator in Rust before. Oh yeah, chip 8 is a pretty common, good project to learn a language, right? I've seen this. I haven't done it before, but I've read about it. How to create your very own chip 8 emulator. There's a bunch of guides out there on that. Yeah, this is the one I was reading a while ago. You're on chapter 7. Oh yeah, okay, that's good. It gets hairy down here. I don't know if you've seen my fumbling through this area of the code, but it gets kind of hairy. All right. Okay, so we have the variable of the name of the class on the stack, and we compile the methods. Preceding call to define variable pops the class, so it seems silly to call named variable to load it right back onto the stack. Why not simply leave it in the stack in the first place? We could, but in the next chapter, we will insert code between these two calls to support inheritance. At that point, it will be simpler if the class isn't sitting around on the stack. Okay. But we could have done that in that chapter. All right, I'm not going to worry about it. This means that when we execute each op method instruction, the stack has the method's closure on top with the class right under it. Once we've reached the end of the methods, we no longer need the class and tell the VM to pop it off the stack. Okay, so right here, self emit byte, pop code, pop, boom. Putting that all together, here's an example class declaration to throw at the compiler. Except we don't have method yet. Did I miss that? No, that's here. Okay. So we can't really do this yet, but we can put the code here to do it. Brunch. Right, we'll just save that for when we actually have method. All that remains for us is to implement the runtime for that new op method instruction. First, we define the opcode. All right, so in chunk. And then down here, we have to add it to opcode method. Add it to the disassembler. It's a self, that's a constant instruction. That's pretty simple. And then interpreter, pop over here and say opcode method is define method, read string. Oh, and then we have to write a define method. Okay, self define method. Of course, read string is a little more complicated for us because we need to pull it here. This is the way we do read string. Let method name is this, and then we just say self-define method name, right? And it takes an obj string. So let me see what's the value of this thing. If I hit Shift K, is that going to work? It is a string. Okay. I'm going to pass it by reference then. And then after close up values. Ooh, I don't have close up values. Oh. That just turned into a pop. So I just put it here. Huh. Interesting. Okay, so now I don't know where this can go in this grand scheme of things. I'll just shove it over here. Define method self and name string. So we're going to get the method as peak 0. We do have to do some fancy footwork in order to do peaking. I'm just scanning my code to see how I did it before, so I don't have to reinvent it. Peak. Oh, okay, so I can just say that. Let value, method is equal to self peak 0. Let class is equal to, I have to deconstruct now self peak 1, right? If let value class equals self peak 1. How did I do it here? Yeah, see, I do this, but that's not the peak version of it. Borrow clone. That's the way I have to do it. And then change that to some class else none. And now we have to check to see if this is actually a class, right? There's going to be error checking somewhere? Maybe not. So table set class methods name method. So our class now, I'm just going to do an unwrap on it, because I'm going to assume that it's a valid class. And it's just a table set. So this is set method or add method. And it gets the name, which gets passed in here, and the method, which we peeked, which we actually have to do a borrow clone. How did that peek? Yeah, see, I'm able to do self peek here without having to do a borrow clone on it. It does pass an RC ref cell value. Oh, the reason is because I'm doing a set up value, which takes this RC ref cell value. Right, so this is the thing I was talking about at the beginning of the stream. Basher said I need to go now. Have a good one. Thanks for swinging by though. Appreciate it. Let's see. Right, so I was looking at did I not save it? No, I must have saved it. Chunk compiler class instance. What did I put? Right, so in the class code, this is what I was looking at. Class code. Here we go. I put this as a closure. And here what we have is the method, which is going to be a value, right? This is a value, if I look at it. Yeah. So that's the thing. Should I put a value in here, or should I destructure that value into the closure itself? Like I do here. That's an option RC class. It would mean cloning the method out. So I guess we can just put the value here, right? Change that to value and just put this like this. If I pass it by reference, and then in here we need to say pub fun add method mut self. That's not going to work, right? We won't be able to do that. Yeah, that's why we need to do the ref cell thing, because this is borrowing it as mutable, and you can't do that. Watch. Self name string value self insert methods insert name value clone. Right. So we're doing this here, and then pop, and we need to do a self pop. Don't forget the pop. Expected struct string found string. Oh, okay. I guess we could just pass the whole thing in. That would mean, yeah. Let's just do. I guess this is where toOwned comes into play. Just cloning. Yeah, cannot borrow is mutable. So this is where we have to go here and make this a ref cell. And do that up here, use standard cell, ref cell, and then say methods, borrow mute, insert. And then mute goes away. And then the ref cell, new hash map. Yeah, okay, so that works. It's kind of frustrating to have to do it like that, but there you go. Interior mutability for the win. All right, so the method closure is on top of the stack, above the class it will be bound to. We read those two stack slots and store the closure in the class's method table. Then we pop the closure since we're done with it. Note that we don't do any runtime type checking on the closure or class object. The asClass call is safe because the compiler itself generated the code that causes the class to be in that stack slot. Okay, so that's this thing, This is the method name. The asClass. Right. This is safe. So this should be a panic, right? Compiler bug. No class found at stack 1. I guess -2. Yeah, okay. The VM trusts its own compiler, except I'm not going to. Okay. After a series of op method instructions is done and the op pop has popped the class, we will have a class with a nicely populated method table ready to start doing things. The next step is pulling those methods back out and using them. The VM trusts that the instructions executes are valid because the only way to get code to the bytecode interpreter is by going through CLOX's own compiler. Many bytecode VMs like JVM and CPython support executing bytecode that has been compiled separately. That leads to different security story. Maliciously crafted bytecode could crash a VM, or worse. To prevent that, the JVM does a bytecode verification pass before it executes any loaded code. CPython says it's up to the user to ensure that any bytecode they run is safe. Nice. All right. Most of the time, methods are accessed immediately called, leading to this familiar syntax: instance.method of argument. But remember, in LOX and some other languages, those two steps are distinct and can be separated. Bar closure equals instance.method, closure argument. Since users can separate the operations, we have to implement them separately. The first step is using our existing dotted property syntax to access a method defined on the instance's class. That should return some kind of object that the user can then call like a function. The obvious approach... One second. Sorry about that. Okay, the obvious approach is to look up the method in the class's method method table, and return the object closure associated with that name. But we also need to remember that when you access a method, this gets bound to the instance the method was accessed from. Here's an example from when we added methods to JLOX. Yeah, we don't have this yet. This should print Jane, so the object returned by .sanename somehow needs to remember the instance it was accessed from. Yeah, we won't be able to do this until we get to this code. In JLOX, we implement that memory using the interpreter's existing heap allocated environment class, which handled all of the variable storage. Our bytecode VM has a more complex architecture for storing state. Local variables and temporaries are on the stack, globals are in a hash table, and variables and closures use up values. That necessitates a somewhat more complex solution for tracking a method's receiver in JLOX and a new runtime type. When the user executes a method access, we find the closure for that method and wrap it in a new bound method object that tracks the instance that the method was accessed from. This bound object can be called later like a function. When invoked, the VM will do some shenanigans to wire up this to point to the receiver inside the method's body. Here's the new object type. Alright, so now we're going to create a bound method. It's going to take a receiver value and a reference to the method of the closure. So this is making me lean back towards making this an RC of closure. Alright, so let's do this. Value bound RC. What should we call it? Bound method. And it's going to take the receiver and method. So I guess we can just call it properly here. And it's going to take pub struct bound. Bound method is going to have a receiver, which is a value, and a method, which is a closure. I'm really leaning towards this based on what I've done before. So use create value star and use closure and use standard RC. And then over in main we have to mod it bound method and then see if it builds. It doesn't. Oh, because I need to use create. Oh, I did. Oh, because it doesn't have a it's not debug. Okay. All right, and now we have to add it to all of these guys. Okay. There. And then display. So how do we print it? I guess we'll get there. I'm just going to scan forward to see if we have a print function. All objects support is printing. A bound method prints exactly the same way as a function. From the user's perspective, bound method is a function. So it has a single method in it. All right, so I guess from this point of view, we can just print it and then we'll implement display for it. Right, and we don't have it implemented yet, so oh, I have that? Oh, because I imported the whole thing, okay. Display for bound method. And right now, this is just going to be a to-do. Like that. Oh, and I forgot to add display. Okay. So we have the warnings only because we're not using things yet. But so yeah, I think we're going to want RCs for our class. Like that, because I think we're going to want to copy the RC into this bound method business. Let's read ahead and see what's going on. It wraps the receiver and the method closure together. The receiver's type is value, even though methods can be called only on object instances. Since the VM doesn't care what kind of receiver it has anyway, using value means we don't have to keep converting the pointer back to a value when it gets past to more general functions. The new struct implies the usual boilerplate you're used to by now, a new case, right? A macro to check its type, another macro to cast, a function to create a new one. All right, so that's what we're going to have to write. Impl bound method pubfun new, and it's going to take the receiver, which I'll clone out of this, and then the method, which is going to be an RC to a closure. And so this will just return self. So self receiver is receiver.clone, and method is RC clone method. Can I do that? and spell this correctly. All right, it took that. Right, so that's just that, allocate the object, and then freeing the object, and then this is in blackened object we don't have to worry about. This ensures that the handle to the method keeps the receiver around in memory. So this is part of the whole garbage collection thing I did in the last stream, which we don't have to worry about. Tracing the method closure isn't really necessary. The receiver is an object instance which has a pointer to its object class, which has a table for all of its method, but it feels dubious to me in some vague way to have object-bound method rely on that. All right. And then there's a print, which we haven't done yet because I didn't have this. So closure has display, right? We implemented display for closure, which just goes to the function, right? So we can just rely on that. We can say write bang f comma this, and then self method. Right, and that's going to call this guy, this is going to call this format, which is going to call this format. So that's going to do essentially the same thing. Right. We don't expose that the VM implements bound methods using a different object type. So put on your party hat because we just reached a little milestone. Object bound method is the very last runtime type to add to CLOCs. You've written your last is and as macros. We're only a few chapters from the end of the book and we're getting close to a complete VM. All right, so we're down to 2 warnings, probably again because we're not using bound method anywhere. Let's get our new object type doing something. Methods are accessed using the same dot property syntax we implemented in the last chapter. The compiler already parses the right expressions and emits op get property instructions for them. The only changes we need to make are in the runtime. When a property access instruction executes, the instance is on the top of the stack. The instruction's job is to find the field or method with the given name and replace the top of the stack with the access property. The interpreter already handles fields, so we simply extend the object property case with another section. So here's get property. So this is this. If this fails, then we're going to call bind method instead of doing this business here. So do we do it this way? If not self bind method instance dot unwrap dot class name. Oh, I used the word field name here. Then we do, oh, if not this, then do return runtime error. Okay, and we have to write bind method because we don't have that yet. All right, I don't think this is going to work though. What type is instance? It's a sum. It's some RC instance. So I can't just call class on it. I think we need to return the actual class. Get class on that. Which means we need to write that pub fun get class self, and then we're going to return RC class self RC clone self class ampersand. Right, so the only error is bind method doesn't exist. Okay. We insert this after the code to look up the field on the receiver instance. Fields take priority over and shadow methods. So we look for field first. If the instance does not have the field with given property name, then the name may refer to a method. We take the instance's class and pass it to a new bind method helper. If that function finds a method, it places the method on the stack and returns true. Otherwise, it returns false to indicate a method with that name couldn't be found. Since the name also wasn't a field, that means we have a runtime error, which aborts the interpreter. Okay, so this is going to be kind of interesting. We're pushing. Oh, I see. We're creating the bound method at runtime. So we're going to pull the closure out of here. Out of the method that we get from the class. And then we're going to bind that. Okay, so this is where things need to line up, right? So if we look at our closure, if we look at the method, which is the value that we get in the methods table, right? So if we look at our class, this is going to give us a value back, right, with the method. Inside the method is going to be the value is going to be a closure. So this might just work out, right? Because if I look at value, if value is a closure, we're going to get an RC of a closure, which we can then just clone to pass into the new bound method. So this might just all work out. So after call value, we're going to add this code here. Bind method. We're going to take in a class, which is saying it's an object class. What are we actually passing into it? Bind method. This is going to return an RC to a class. That's fine. So we can just do that. And then the field name is a string, right? Not an ob string, just a regular string. Like that. And returns a bool. All right, so the first thing we're going to do is we're going to get the method from the class. So we're going to say if let some value. What are we putting in the class? It's a closure, right? These are all closures. Method equals class.get method. Class get method. Then we're going to do this work, otherwise, else, and return, self runtime error, undefined property, this, and it's going to be name chars. Oh, I can just stick it in here. Right, and then return false. If this happens to return false, we're going to see undefined property name and an undefined property field name. So that's a little awkward, right? Otherwise, we're going to say, we're going to create this new bound method, let bound equals bound method new peak 0. Now peak 0 is what? Oh, we don't have that. It's supposed to be the value. So we're going to have to get let value equals self dot peak 0 dot borrow dot clone, and then pass it in here, value, and then method. This might have to ampersand as well. And now we have the bound method. We say self pop. We say self push. Bound. Oh. When we push, we have to push a value, right? Value, bound, bound. And then return true. Like that. What's going to break now? Unclosed identifier. Okay. Not found in the scope. Bound method. And field name. Doesn't like that. Expected that. Expected function found RC class function. Class has type RC class. Call expression requires a function. Oh, class document. What am I doing? Okay. And oh, I don't have get method yet on class. We have add method. Hub fun get method. Self. And it returns a. Oh. Yeah. So this is where things break down, because we want to actually add. We want to actually get the method that's actually the closure. We can extract it here, right? We can say let closure is equal to, no, if let value closure equals value, then closure, it should, this should be an RC of closure, right? Yes. And we can just clone it right here and put it there, and then this can be an RC of closure. Right, use create closure. Yeah, I figured we'd have to do that eventually, right? And then this can return an RC of closure, which is just going to be, oh, an option. RC closure, oops. And which just says self methods borrow get, got the name. Probably not, but let's find out. RC's not found. Use standard RC. Diablo, yo, how are you? I wish the chat on my chat doesn't have timestamps on any of these chat messages. I don't know why. Be nice to know how late I was with responding to you. Expected option doesn't the get return an option? Oh, it returns an option reference. And there was something we did to switch things around from to swap that around, and I forgot what it was now. To owned, cloned. Okay. Get method name. And now this doesn't, oh, right. So now we're not expecting some value closure, we're expecting some method there. And bound expected RC. Oh, what is push? Push expects a value. Oh, the interior here expects RC. RC new. Clone. Does it, what does this return actually? What does this return? This returns just a bound method. Okay, so we do need to RC it. Okay, and now this has a problem because we're moving what's 149 Move occurs because the instance has type option RC instance. 166 is, oh, I see. We can't reuse it because we just extracted it here, so now we can't use it there again. They're suggesting using an as ref on 166 so that we can use it again. Will that work? Well, I mean, it made the errors go away. We're not using receiver, and we can't get. Oh, runtime error has a result. Oh, that we have to return runtime error. 417. That. Okay, we'll just ignore the error. I mean, I guess what I could do is just make this a result. Interpret. And just make this okay true. Oh. No, I'm just going to leave it alone. That's the simplest thing to do, because actually what we could do is make this a result, right? And just have this do the error path and just do okay true, and then we change bind method. Instead of checking like this, we just question mark it. But then, I don't know, we have to make sure the errors line up, otherwise the test suite, the Dart test suite won't work out. Where was I? Over here. So this builds, the warning is we're not using receiver, right? Yeah, which I'm assuming we're going to get to any second now. First, we look for a method with the given name in the class's method table. If we don't find one, we report a runtime error and bail out. Otherwise, we take the method and wrap it in a new object-bound method. We grab the receiver from its home on top of the stack. Right? Finally, we pop the instance and replace the top of the stack with the bound method. So we should be able to do this. I don't think this is going to work yet because it's blocks. Because we're not doing anything with receiver yet. Yeah, I don't think this is going to work yet. Okay. So this is what's happening, right? When we bind the method brunch eggs to eggs. This gets a receiver, it gets the method to the same closure that eggs points to, and then the receiver is pointing to the class, that the instance of the class that we're talking about, which is the brunch in this case. All right, that's a lot of machinery under the hood, but from the user's perspective, they simply get a function they can call. Users can declare methods on classes, access them on instances, and get bound methods onto the stack. They just can't do anything useful with these bound method objects. The operation we're missing is calling them. Calls are implemented in the call value, so we add a case there for the new object type. The bound method is a first-class value, so they can store it in variables, pass it to functions, and otherwise do value E stuff with it. So if we look at call value, we're looking here, we're going to say value bound method. Return self call. I don't think we can do that. We can try it. Arg count, just like closure. I don't know if this is going to work because, well, let's find out. I mean, it doesn't complain. We pull the raw closure back out of the bound on the object bound method and using the existing call helper to begin invocation of that closure by pushing a call frame for it onto the call stack. That's all it takes to be able to run this locks program. All right, so this should work then, right? If this is correct. And if this is correct, I'll just move it down here. Maybe this will work because what's on the top of the stack is already a closure. Yeah, So that should work. Fingers crossed. What are we going to call this? Scone? Oops. Of course I did. Copy. Paste. Cargo run scone. So this should print scone with first and second. So berries and cream. Let's find out what happens. We're still not using receiver. And it panicked. No class found at stack -2. There it is. It's at... We tried to do topping. We tried to put the topping method in, but this didn't work. Because it looks like it's looking too far back, right? It's expecting the class name to be 2 back on the stack as opposed to 1 back on the stack. And I've forgotten where in the code. Oh, it's right here. Define method. So we're in define method. Right? Source VM. Did I forget a push somewhere? No, there's op method, define method, read string. I guess we can start debugging stuff here. Println define method name. And then we can say println method equals method or class, right? This should be, oh yeah, that's something. And then this fails. So whatever is back there, we should print that out. Println debug, and we'll just say self peak 1 and see what that is. And what did I mess up? Oh, here. There, okay. Cargo run is gone. Define method topping, and then see, it's expecting to see right. So what's happening is it's looking here and finding the script instead of here. For some reason, the method itself hasn't been pushed onto the stack. So did I miss? Because that's what needs to go on there, right? We have op class, define global, get global. Oh, I'm missing this here, this closure business. Did I miss a step? Here's op method. This is initializing the table business, and this is the beginning of the thing. So we're missing a step here, right? We're missing this closure. Because this op method is supposed to take this closure and stick it here. So where do we push the closure onto the stack? I must have missed it, right? Let me look for all the push calls. That's in there. Is it this here? No, bind method. This is after. Right? Let's take a look at bind method, make sure I got that right. This, yeah, so I push this value bound on here, okay. Here's another push. That's calling it. Oh, this is past. That's this thing. This is saying this is all it takes to be able to run this locks program, right? We can declare access in invoked method, but something is missing. We went through all that trouble to wrap the method closure in an object that binds the receiver, but when we invoke the method, we don't use that receiver at all. Yeah, Rust told us that. We're not using the receiver at all. But we're still missing. We can't actually do that. I don't know if I should just barrel on and see if this problem gets solved. But based on, where was that? This, right? Here's what the compiler generates and how those instructions affect the stack at runtime. And we saw everything except for this op closure instruction. So we're missing this somehow after get global. Let's take a look here. It's there. It's just after op method. We have op class, define global, get global. Then it should be closure, and then method. Here's where op method comes out. And that comes out here between the open brace and close brace. So wait a second. This is the table stuff, and that's the beginning. Okay, so where does this come out? That's on line 4. 2, 3, 4. So here is when we define the closure. We do the method first and then the closure. Something's wrong. Here's where we output the method, then we call function type, and then op method. Oh, maybe that's it. Maybe that's it. Maybe I put that in the wrong spot. Yeah, I did. Look. Okay. That's the bug. So now let's get rid of those print statements in the VM. Okay, cargo run scope. Still panicked. Try to call a non-function. And that's VM line 355. Okay, so this is the issue that I was having before, or was thinking about before. We can't. Yeah, the top is not a closure; it's a bound. So maybe what I need to do is say bound method. Yeah, see, this is where things get a little wacky. Okay, so there's a bunch of places we use call. We use call here, but it's not this call. That's the call on the native stack. There's a closure call. And the class doesn't, when we call a class, all we're doing is creating a new thing. So maybe what we need to do. Oh, and I think the reason I was having problems is if I did this, if I said closure here, and then tried to pass it in here, we ended up with issues of, what's going on? Yeah, we end up with issues of, but this is an RC, of borrow checking. Let's just try refactoring this here real quick and see what happens. This should be that's a closure, right? And then this just changes to arity. Let's comment this out. Arity is equal to closure arity. And see what breaks. Oh. Right, so we're pushing this new function as a closure and then calling it. All right, which means we have to break this into 2 steps. Which is probably a good idea anyway. Let closure equals RC new, closure new, RC new function. And then this just becomes function with capital lowercase n, and then this closure here becomes RC clone closure. Still have a lot of closes, and then this becomes a call to RC clone. Oh, no, but we'll just pass it in directly, closure. Nope, expected 2 arguments. What's the other argument? Arg count. Okay, and then we can say method dot, what is method? Method dot method. Can we get the method? Let's get the method. Pub fun get method or get closure. Self is going to be RC closure, and we'll just say self method RC clone. And this will be method dot get closure with the arg count. All right. So I think that cleans that up, right? And then if this works, then we can remove all of this block of code here. Cargo run. Nope. I mean, it got further. Thread main panicked at no chunk. Oh, right. So when we're doing this, we assume that there's a closure on the stack at position, which is the current frame. Current frame's closure. So when we're calling that, I mean, we got pretty far, right? We got the topping, the berries, the cream, those got pushed, and then we just tried to call it. And I was looking here with the function topping, and it just got the wrong closure, or the wrong stack. Let's take a look here, what we think the position is. Position. Yeah, and then run that. Position is 1. That's correct. So that should be a closure, right? Oh, it's not a closure, it's a what's on it? Let's find out what it is. I think it's the it's not a value closure anymore. It's a, well, let's find out. Print line. I should just throw it in here. Debug of self stack position. Whoa. I was not expecting that. It's a ref cell value closure. So isn't that what we're expecting, a closure? Oh, it's the last one that failed, right? Here. Yeah, it's a bound. And we should be able to get the closure from the bound. Right? Yeah. But there's two different. Value topping is a closure. And method closure. Oh, we should be able to get the bound method. Okay. Whoops. What am I doing there? So here, it's not a value closure, it's actually a value. So we can say match self, stack, position, borrow, deref. And that's going to be value closure. It's going to be C get chunk. If it's a value bound B, then it'll be B dot get closure get chunk. And then anything else is panic no chunk. What format? Oh, that's right. I can do was it space F? Nope. I thought I had that set up. What did I do wrong here? This should be a comma. Deref. Okay, we still have the receiver thing, but maybe this will work. Oh, did I get rid of the print? I gotta get rid of the print. I don't want to see any of that. Okay. So cargo run. Let's go on the tail. Well, it didn't panic, but I didn't see the whole thing, so let's get rid of that. Yeah, scone with berries and cream. Okay. Diablo says, looks like the book knows. The book knows that I screwed up. But yeah, so the first mistake I made was I put function type after emit bytes instead of before emit bytes. So that made this thing come in the wrong order. And the second problem I had was a personal problem. So to speak, something that I had written here to get the current chunk. And of course, if you have a bound method on the stack instead of a closure, I guess what we could do is just push that or put that on the stack instead. But this seems like the bit straightforward. You said that before I put it in the wrong order? Yeah. Okay. Yeah, sorry. When I'm focused on this thing, I ignore chat, and that's bad. I should have something play a little ding whenever somebody chats, because otherwise I miss it. All right, so we're up to, we did 28 1 and 28 2, and we have something working now. Clippy has a few things for me to clean up. Receiver I'm going to ignore for now. You should. So, Diablo, I didn't know you streamed. What kind of stuff do you stream? So let's fix this. Writing string instead of start involves a new object. Okay, so let's 23. So will that build? See, now it won't build, so we have to say toString. Okay, and then the next one is in class. Oh, I was already in class. Get method and define method should both be stir. Are there games or coding? Okay. I'll have to. I don't think I follow you. I'll have to add you to my follow list. There we go. The next time I see you, I'll hop on, say hi. Bind method in VM. and then define method in VM. So that should improve performance a little bit. Yeah, and I don't care about that guy. So you know what? We can do this. What is it? Is it ignore or allow? It's called allow, right? Yeah, okay. So now git status, git add source, git commit. Sections 28.1 and 28.2. And they were called, I'm going to scan back here because I'm going to cheat. Methods, declarations, and references. Method, declarations, and references. And that's gonna wrap up my stream, I think. Yeah, this is a nice stream, a nice easy stream. One of the things that when I write my own interpreter, which I'm gonna do, there's no reason to go through all this and learn how to do it and then not do it. I just got to figure out what I want to interpret. Probably something simple like basic. Got to write tests along with it. Okay, so then tomorrow I'm going to get back to the editor, and then next week we'll resume. On Monday I have off, so I'm not going to stream Monday. So tomorrow's the editor, and then next week we'll get to this, which is 20.3. So let's push this up and call it a stream. There we go. Let's take a look over here. There we go. Nice. Nicely done, if I do say so myself. Okay. Well, have a great day, everyone, and I will see you next time with the editor code. All right. Take care.